Hi, everybody. Dr. White back again with one of the most spectacular results of the entire course, the Central Limit Theorem. So recall this. When you got a random sample of size n from some distribution, and maybe it has mean mu and variance sigma squared, okay? Then you know the expected value of the sample mean is mu, and the variance of the sample mean is sigma squared over n. A consequence of that would be that if you took away mu and divided by sigma over root n, the variance, the mean would be 0 and the variance would be 1. Let's just make sure that we can convince people of that if somebody asks. So like, what is the expected value of x bar minus mu over sigma over root n? Well, expectations linear operators, you can factor out constants. They're linear operators, so you can distribute over the minus. But the expected value of x bar is mu. So you're left with a mu minus mu because the expected value of a constant is constant. So you get a 0. And as far as the variance is concerned, you've got here the variance of a random variable on the top, and you can think of it as multiplied by 1 over sigma over root n. But the variance of a constant times a random variable is the square of that constant times the variance of that random variable. So you're left with the variance of x bar, which is sigma squared over n, times 1 over sigma squared over n. So you're going to get 1. So the same. Could we say any more about the distribution of x bar? And there's a typo there. That should be x bar right here. Could we say anything more about the distribution of x bar? And there's a theorem that says, yes, if the sample size n is big enough, then the x bar that's based on that sample, you can say a lot more about it. Here's what the theorem formally says. For any w in the real numbers, if you look at this random variable, x bar minus mean, this mean over the standard deviation, and ask for the probability that it is less than w, okay? Find that probability. And then you take the limit as n goes to infinity. And so what you're doing is you're basing your x bar on bigger and bigger and bigger samples. That's 1 through xn. Then those probabilities are going to converge. And what they will converge to is the probability that a standard normal is less than or equal to w. So what this theorem is really saying is that in the limit, the CDF for x bar minus its mean over its standard deviation is the same as the CDF for standard normal. So they're saying informally that x bar minus its mean over its standard deviation gets closer and closer to standard normal. I've got another typo there. That should be an x bar. Fix that. Okay. So another way to put that is instead of talking about kind of the standardized version of x bar, you could just talk about x bar. If the standardized version of x bar is getting closer to standard normal, then x bar is getting closer to just normal with the mean of mu and the variance of sigma squared over n. Or if you just want to focus on the sum of the xi's at the top of the x bar, well, we know the sum of the xi's would have a mean of n mu and a variance of n sigma squared. What this theorem is saying is that that sum is approximately normal, and that approximation is going to get better and better and better the bigger the sample size is. So your next question probably is, well, how big should the n be so that that approximation really takes hold and appears to be good? How big should n be for that to be close to standard normal? Or for the x bar, to be close to normal, or for the sum of the xi's to be close to normal in mu, the variance in sigma squared. I think that looks like another typo. I don't quite see a bar over that x right here, so I just fixed that. So let's investigate that by working with some simulations, and it comes, you've got to enter this URL to get to an app that I wrote for you. So let me head to a browser and do this. So homer.shinyapps.io/central limit. Okay, and it says wait while it sets itself up. Okay, so here's the situation. You get to choose between 4 populations. So imagine 4 big populations, and each of them has a different shape. And when you pick an item from such a population, and measure your item, you got a random variable, okay? And in one case, your random variable is normal because your underlying population, if you make this thin bell shape. In another case, you'd be looking at a kind of a right skewed population, okay? And in another case, you're looking at an extremely right skewed population. I believe this one's taken off of something called the Pareto random variable, which has a huge tail going off to the right. And you can also, this 4th population is one where I think it's like 90% of the population is somewhere around 50, and another 10% is somewhere around 200. Okay, so those red density curves indicate the PDFs of 4 different underlying random variables from which you can take random samples. So I'm going to just switch to normal right now. And so here, the underlying random variable is normal with mean 70, and I think the standard deviation looks like, let me go to the point of inflection and go over. It looks like the standard deviation is about a 3. Okay. And what you can do is you can take random samples from this population, but you can pick your sample size. I'm just going to go ahead and pick like a sample size 10. And I'm going to take one random sample of size 10. I'm going to do that right now, sample now. And so it makes here in blue a little histogram of the 10 random values, x1 through x10, that it picked out. And in the little blue dot is the sample mean, x bar. Okay. And so as you can expect, x bar came out to be somewhere around the mean of the population. And I can just keep on sampling. So I'm going to sample again. Here comes another sample of size 10. The x bar was a little closer to 70. There's another sample of size 10, another x bar. And as you might expect, the samples being random samples from the underlying distribution, a histogram for the samples might be kind of roughly similar in shape to the shape of the random variable itself, but that's going to be pretty rough at sample size only 10. So I just keep on taking a few. And as I go along, I can go over to see where it says sample mean distribution. What I've got here is, you see this little rug of, you see this like rug of little sticks at the bottom, those are my sample means from all of the random sample of size 10 that I've taken so far. And the blue that you see right here is a density curve based off of those sample means. And so what it's trying to do is estimate the distribution of X bar. It's trying to estimate the PDF of X bar. The red is the real PDF of X bar. Now, since we're sampling from a normal, we know that X bar is normally distributed with mean 70, mean of the underlying random variable, and variance, well, if the standard deviation is 3, the variance is 9, divided by 10 sample size. And so that's a normal curve, mean 70, variance 0.9. And as you can expect, the estimate of the PDF based on our X bar so far is not too far off of that. Now, if you get a little bit impatient and you'd like to not just do one sample of size 10 at a time, you could do a lot at a time. You could do as many as 10,000 at a time. Let's do that. So that's throwing on another 10,000 sample means from this underlying distribution. The blue dot here is the latest sample mean, the very last of those 10,000. I'm not showing a rug anymore because now there's like 10,000 plus whatever, however many I had before. But notice that the blue density curve is now very close to what we know is the true distribution of X bar, normal with mean 70. Okay, so no surprises there. That just confirms what we learned in the last section, that when your underlying distribution is normal, your sample mean is normal, same mean as the underlying distribution, variance is sigma squared over the sample size. That's going to work like no matter what sample size you were to use, as long as the underlying distribution is normal. But what's interesting, what the central limit theorem addresses, is these other times when the underlying distribution may not be normal. It could be anything, as long as it has a mean and a variance. The central limit theorem claims that if the sample size n is big, that the distribution of X bar is approximately normal. So let's try it out with this skewy population. The mean of this skewy population is 100. That's what the vertical line means. And let's give myself like a smallish sample size. How about sample size 5? Come on, 5. There we go. And let me go ahead and just take 10,000 samples of size 5 all at once and compute the 10,000 X bars and throw up a density curve of them. Okay, so we'll sample. And here we are. The blue is a density curve of my 10,000 sample means. It's all based on samples of size 10. That's the latest one. It came out to kind of far from 100. But notice how bell-shaped the density curve for those sample means is. What I've drawn in red is a normal curve with mean 100 and variance equal to the variance of the underlying population divided by the square root of 5. So you can see there's definitely a difference here. It looks like the distribution of X bar is really not quite normal. It's kind of skewed more to the right, just like the underlying distribution was. I can take another 10,000 samples and another 10,000 and another 10,000. So I've now done like 40,000 X bars. And so this blue density curve here is a mighty good estimate of the real PDF for X bar. And you can see it's not quite normal. It's a little bit skewed to the right. It's going to start over. But let's bump the sample size up here to, maybe 50. And now let's try. Ooh. And now the density curve for X bar is pretty close to normal. And what the central limit theorem says is if you could bump the sample size up higher, if you could have your slider go past the 50, the n is 50, then you would see that your blue density curve is getting closer and closer and closer to that red curve that they show. It's perfectly normal. And so, like, when would you be satisfied with the approximation afforded by the central limit theorem? Like, what sample size is big enough? A lot of people say that 30 is big enough. And they base it on doing simulations like this. Let's just see how that would be. Let's try 30 here and grab 10,000 X bars. And you can see why they think 30 is big enough. That looks good enough to me. Looks pretty good to me, kind of intuitively. But you should be careful about that rule, because if your underlying distribution is real heavily skewed, or if it has some outlier portion to it, then 30 may not be satisfactory to you, may not be big enough. You could experiment with the really skewed population yourself to see what you think. Do you think 30 is big enough? I'm going to experiment with the way out outlier group here. So I'll go ahead and start with some small sample size, like sample size 5. And but let's take a look at the population we're sampling from. The mean is right here with this vertical line, so that looks like around, it's a little bit over 60 or something. But there's kind of like an outlier component to this random variable. In fact, this random variable is a mixed random variable, as we've learned about these before. I think there's like a 90% chance that you pick from a normal distribution with mean 50, and a 10% chance that you pick from a normal distribution with mean 200, and that formed this underlying random variable. Well, anyway, we're going to take a bunch of samples of size 5 from it and get the X bars and see what they shape up to be. And it looks awful. The PDF for X bar looks like this kind of doohickey in blue, as opposed to a normal curve with mean equal to the mean of the underlying random variable, variance of the random variable divided by sample size 5. They're just very different. And you can kind of see why it has those bumps, because what's happening is, like, in a sample of size 5, quite often you'll never get anybody near 200. And so your sample mean will be near 50 a lot of the time, and that's why there's so much height here. But, sometimes you'll get 4 that are around 50 and 1 that's around 200, and then your sample mean is going to be a lot bigger, and that's the cases that fall kind of in here. And I guess this must be where you got 2 of your 5 being near 200. And I guess this is where you got 3 of your 5 being near 200, and so on. Anyway, the point is that the central limit theorem really has not had a chance to take hold at such a small sample size. So let's start over and give ourselves a sample size of 30 that people say is big enough. Grab 10,000 of these X bars, and I'm still not satisfied. I'm starting to see, like a hump taking shape in the distribution of X bar, but I'm still not seeing closeness to the to a normal curve. What about size 50? Well, it's better, but it's still not acceptable as an approximation. So you do have, there's that one caveat in applying the central limit theorem, to compute probabilities for a sample mean. Your underlying distribution, if it's really skewed one direction or the other, or if it has these crazy outlier components like this one does here, then the approximation may not be as good as you like. You might really need high sample sizes before it's acceptably good. Anyway, interesting to play with that out. Back to the notes. How about an application? Let's say that x1 through x18 is a random sample of size 18. The underlying distribution is chi-squared with 1 degree of freedom. Well, we know that if you take the sum of the sample, that's chi-squared with 18 degrees of freedom. So we know everything about probabilities for the sum. But if we didn't know that bit of statistical theory, we could try to use the central limit theorem to approximate probabilities for the sum, capital Y, because it's the sum of 18 independent samples from an underlying distribution. It's a sum. It's a sum of random sample, and so we could try to use the central limit theorem and approximate it as normal, with mean equal to the mean of the sum, so that would be n times the mean of the underlying distribution. Let's see, chi-squared with 1 degree of freedom has a mean of 1. 18 times that is 18. Okay. And what would be the variance? Well, it would be 18 times the variance of a chi-squared 1. Well, the variance of a chi-squared with 1 degree of freedom is twice its degrees of freedom. 2 times 1 is 2. So 36. All right. So let's just see how well that approximation might work. You could go to R and you could get the exact probability, because you know that this is chi-squared with 18 degrees of freedom. What's the probability that the sum is less than 24? T chi-squared 24 df equal 18 would give it to you exactly. Okay. It turns out to be 0.8449. But if you use the normal approximation, then you would head for P norm. What's the chance of being less than 24 in a normal where the mean is 18 and the standard deviation is the square root of the variance, 6? So that's the approximation suggested by the central limit theorem. And that comes out to about 0.8413. So not bad. Even though 18 is a bit, smallish, it's below the 30 that a lot of people recommend. The deal is that a chi-square 1, although it is quite a skewed right distribution, it's not skewed right so bad that the approximation is terrible in this case. Let's try another one. Say that you have some random variable that has a mean of 30 and a standard deviation of 3, and you take a random sample size 100 from it. Pretty big sample size there. What's the chance that the sample mean would come out bigger than 29.5? I mean, you'd expect the sample mean to be around 30. So I'm expecting an answer here that's definitely bigger than 50%, I would say. Well, X bar is going to be about normal with a mean of 30 and a variance 3 squared over the sample size. Okay. So the central limit theorem is suggesting that approximation. So let's give it a try. Well, the chance of being bigger than 29.5 would be 1 minus P norm 29.5. Mean is 30. Standard deviation is square root of that stuff, which is 3 over 10. And you get 95%. So another simple application of the central limit theorem. That's all I got for now. Well, no, it's not all I got. I want to bring you back. Let's head back to R. And I want to bring you back to that thing we were noticing all semester long about a lot of our random variable families. Let's go to BCSR : disk explore. BCSCR, disk explore. And I'm going to kill my face. So like think about binomials and think about how often their distributions look normal. You know, they look bell-shaped. And, you know, we had noticed that a binomial with n trials, chance of success p each time, is the sum of n independent Bernoullis, each of them chance of success p each time. So a binomial is the sum of a random sample. It's a sum, I goes from 1 to n of the xi's. And the central limit theorem says that if the n is big, that sum should be approximately normal. That's why we're seeing these kind of bell shapes when the trials go high. Like even if you had some weirdly small probability of success like 0.01, if you bump the trials up big enough, you still get bell shape. It's really the central limit theorem that's telling you that. Or think about negative binomials, you know? So here's where you're waiting for just 3 successes in a Bernoulli process where your chance of success is 20% each time. And you got this pretty right-skewed distribution. But a negative binomial where you're waiting for S successes, it's the sum of S independent geometrics with that same chance of success on each one. And so as a sum of random sample from a geometric distribution, if the size of the sample is big, then the distribution should be normal. So let's take a bigger random sample. Let's take 21. And so there, where you're looking at the sum of 21 geometrics, the sum of a random sample of size 21 from a geometric distribution, you get more of a bell shape. Poisson. Okay, so we're looking there at a Poisson with a rate lambda of 3. Remember, lambda is the mean of the distribution. And we had a math theorem. We had a theorem that we proved using the moment generating function technique, that the sum of independent Poissons with different rates is a Poisson with rate equal to the sum of those rates. So I can actually think of this Poisson 3 as Poisson 1 plus Poisson 1 plus Poisson 1. I can think of it as a random sample of size 3 from an underlying Poisson 1 distribution. Now, if I bump up the sample size to maybe sample size 10, you get 10 exactly, there's 10. Well, the distribution just got more bell-shaped. Go up to random sample of size 50, even more bell-shaped. Central limit theorem again. You can see the same thing at work if you look and explore the gamma distributions, again being able to think of gammas as sums, and then from that thinking of them as sums of a random sample and so on. And so that mystery that we saw, that quite often these distributions had sort of a normal shape, I think the central limit theorem is shedding light on that, a great deal of light on that phenomenon. Okay, that's all I've got for today. See you later.